In this lecture, we will talk about two methods side by side. The two methods that we discussed for computing volumes of revolution, namely disks and cylindrical shells. So let us recall what the methods actually are, thinking in terms of the volumes of revolution, or rather just volumes of solid objects. Disks method thinks about that in terms of stacking disks of the same or maybe different radius on top of each other, kind of like a stack of pancakes would be. Whereas cylindrical shells is the thinking of stacking cylinders or very thin cylindrical shells inside of each other, of again, various radius and various heights. What that means for graphs, for example, if we rotate around the x-axis, let's pick some function without an equation. I just want this to be for visual purposes. If we're thinking about rotating it around the x-axis and we think about where that function will end up, once we have that, we need to think of the resulting solid as a stack of these disks. So what we do is we put in a typical disk that has some non-trivial width. So basically, just a really short cylinder of sorts. And then the points on the curve will allow us to describe the radius of the disks, and the thickness of it would describe the thickness of the disk. Now, remember that with disks, the thickness is parallel to the actual axis of rotation, which means that if we're rotating around the x-axis, the resulting integral will be in terms of x. Now, for cylindrical shells, the situation is going to be somewhat reversed. So let's take a look at some function. Again, no need to produce an equation. We're just interested in the visuals for now. So let's say something that looks like this, and I would like to once again rotate it around the x-axis. Now, the first thing to do is produce the mirror image, so something along these lines, and then think of how this solid is now constructed of cylinders, or is now consistent of cylinders. So what we're going to do here is kind of do the exact opposite way of thinking to the disks. The axis of rotation for cylindrical shells serves as a core around which the cylinder is actually situated. So in order for me to draw a typical cylinder here, I'm going to draw along the core, which is the axis of rotation here, and then introduce some thickness to my little cylinder here. So it's going to have some non-trivial thickness here. And then what I of course notice right away is that this thickness is now parallel to the other axis, and therefore my integral is going to be described in terms of y. So whatever axis you're rotating around, for disks, this will be the same as the variable in your integral. And for cylinders, it's going to be the exact opposite of the variable in your integral. And that's, of course, because the shapes are qualitatively very different. The disks are already all filled in, whereas the cylindrical shells themselves are, in fact, hollow, only having non-trivial width to them. Now, this is for two different functions. Let's take a look at how this would work out if I was using two different methods, but to compute the exact same volume of revolution. So here, we're going to compute the volume of a cone that is generated by rotating a line, y equals 1 minus x, with positive y around the y-axis. First, we're going to use cylindrical shells, and then we're going to use the disk method, but the volume really should work out to be the same, right? So first of all, the first thing we always do is sketch it. Remember, do not economize on this step, because only through the sketch here will you be able to actually see the attributes of the cylinders or the disks that you need to include in your formulas. So let's sketch the region first of all. My line is 1 minus x, which means that it's the line with the y-intercept of 1 and the slope of -1. So it's the line that goes something like this and continues on. I am interested in rotating the region of it for y equals 1, and let's say bounded by the x-axis, around the y-axis. So I'm going to rotate this piece of the line around the y-axis. Let me actually include this on the picture, okay? So I'm gonna take this line and I'm gonna move it along. As it sweeps through all the way around, you should be able to visualize that it makes exactly an upside down ice cream cone. So the first thing to do is probably to mirror image this line over so we can see what happens on the other side. This will of course then produce another point on the left-hand side here. And now, because the first method we're going to use is the cylindrical shells method, we're going to think of how this cone, this circular ice cream cone, is actually composed of cylinders. Okay? Recall that whenever you rotate around the y-axis, your shells will be spanning along the y-axis as their core. So in order for me to draw a typical cylindrical shell, I'm going to use some point on my boundary here, take its mirror image, and then draw in the cylinder that is centered on my axis of rotation, which is y-axis in this case, like this. And then I'm also going to give it some non-trivial width because this is what's necessary for me to actually put together these whole bunch of cylinders in order to make the cone. Again, because cylinders in particular are hard to visualize, let me draw in temporarily a few more here. So if I go further up, the cylindrical shell here will be longer and thinner. And if I go further down below, they're going to be a little bit wider and shorter. Okay, so all along here, for every point on the curve, I'm going to have a corresponding cylinder. And depending on where I pick such a point, my cylinder is going to have variable radius and variable height. But the first things first, I recognize that the width of it, the thickness of it, is along the x-axis, parallel to the x-axis, which means that my integral is going to be in terms of x. So recall that the general volume of a shell is given by the formula 2 pi r h times the width. Now the width here, well, let me just write it out as the width. But the width here was the first thing that I determined because this is what's going to allow me to, first of all, fixate on my variable of choice. The width is going to be dx. And now I just have to think of what is the radius and what is the height of my cylinder. So for this drawn-in cylinder, this is a chosen point on my axis, on my boundary, and I have to be in terms of x as the variable. The radius of this cylinder is exactly my chosen variable x, so I can note that. And the height of my cylinder is exactly the corresponding y-coordinate. Y-coordinate, of course, is given to me here as a function of x, so I can simply write that down. So the height of this cylinder is 1 minus x. Now this is the volume of one shell, and in order for me to then compute the total volume, I have to sum up or integrate over all of these shells that compose this cone. So I'm going to take the integral of this expression with all of the pieces that I've just plugged in. So 2 pi x 1 minus x dx. And now I have to think of x, which is my radius. What is the smallest and what is the biggest it can be for my cylinders inside this little cone? So the smallest it can be, of course, is 0. X is going from 0 here. And that will correspond to the 0 radius cylinder, not very exciting. And the largest it can be is 1. This is going to be my widest cylinder at the bottom. It's going to be of height 1. So both of them are trivial in a sense, but have to be included as the endpoints. I'm going to build cylinders of radius from 0 all the way of radius 1 along this line. Now, if we compute this, I do believe the answer will be pi over 3, but make sure that you actually check over my calculations. Now, this is the cylinders method. Let's now compute the volume of the exact same shape using the discs method, just to see how different the setup will actually be. So my picture, or at least my very first picture, should not be different at all. I am, after all, computing the exact same volume. So I'm going to start off with drawing my line. So I have the y-intercept of 1 and the line of slope -1 going through this point. Once again, I am rotating around the y-axis once again. So I'm going to go over to the other side to complete my sketch. And now I have to think of this cone as being generated by a bunch of discs stacked on top of each other. I'm going to draw in a typical disc. So I'm going to pick a point here and simply draw in the disc. Now this is probably, once again, a little bit easier to visualize, as discs usually are. So here I go. And I can see that this is really like a stack of pancakes, right? It's just my pancakes form a very triangular stack being on top of each other with shrinking radius. Okay? So again, first things first, I'm going to think of what is my thickness, and therefore what is the variable that will be present in my integral. I notice that my thickness is parallel to the y-axis, which means that overall my integral is going to be in terms of y. And now, with that information, let me think of the volume of a typical disk. So recall the overall formula for one disk is pi r squared h. Now, h, which is the thickness of my disk here, I already know to be dy. And so now I need to think of my entire integral in terms of dy and recognize what is the radius in this case. So what is the radius of this disk? Well, the radius is going to be, of course, this length. So if I take the point on my line, y equals 1 minus x, the radius of the disk is represented by the x value of it, right? So this has to be, the radius itself has to be x equals something. Now, the thing is, my integral is in terms of y, so I'm going to have to rewrite that in terms of actual y, right? So I have to take my original equation and massage it a little bit to solve it for x instead of for y. Now, this is easy, just switch the variables around, and overall I'm going to get x is 1 minus y, which is why here I'm going to get x is 1 minus y as the radius. Now, this is the volume of one disk, which means that the total volume here is going to be given as I integrate over all such disks. So let's plug in all of this into my integral. So I have pi radius, which is 1 minus y squared. This is my radius, dy. And then again, we're going to have to think of, in terms of dy, or in terms of the radius of my, the disk, what is the smallest and what is the largest it's actually going to be. And I can see that I have to build my disks from 0 all the way up to 1 in terms of y. So these are going to be my limits of integration. Now notice that, of course, I better get the exact same result as before, but notice that my integrals that do produce the same result look very different, drastically different in some ways between the two methods, right? So first of all, the cylinders being rotated around the y-axis produce the integral with respect to x. The disks being rotated around the y-axis produce the integral in terms of y. The integral in this case sort of does not clearly involve the square until you multiply it out, whereas here I have an entire function squared. So integrals and the setup for the two methods will be different, but if of course you're computing the same volume, the final answer better be the same. Now let's take a look at a few more examples here. So I'm not sure what happened between my text and my pictures, but make sure you fix the text as is now on my slides. So I'm interested in rotating the region bounded by y equals square root of x as is drawn, and the x-axis between points 0 and 1. So first I'm going to use the disk method, and then we're going to see how something similar would work out for cylinders. So it's important to recognize what it is that you're rotating, first of all. It's the region bounded by my curve and the x-axis. So I'm rotating the region below my curve between 0 and 1. And first I'm rotating around the x-axis. So I'm going to take this down and rotate it around. This example we've already seen sort of a number of times. But let's go through it so that we can see how it compares to other more complicated scenarios. If I'm going to use the disk method in this case, I have to draw in a typical disk. So I take a point on my curve and I rotate it around with the disk. Here we go. And I give the disk some thickness. There we go. This is my disk, and I'm pretty well set up in order to write down the integral. First thing, I notice that my thickness is parallel to the x-axis, which means that my integral is going to be in terms of x. And recall that for disks, I'm going to have pi r squared, pi times radius squared, and then whatever the thickness was, which in this case is dx, that dictates my variable. So then, all I need to do is determine what is in fact the radius of my disk. And here the radius is given to me by this, the height of my point that I choose to draw my typical disk at, which means the y coordinate, because that's the vertical component of it, which means square root of x. So my radius is square root of x. And then note, of course, that my radius gets squared, so I must square this as well, and the thickness is dx. Then I need to figure out what is the smallest and the largest value of x that can be, and here I'm specifically told that I would like to be between 0 and 1. Excellent. Here's my integral. It says to set it up, not to solve it, because again, we're so far interested in only that as the main step. Let's try to think of what's going to happen if we rotate it around the y-axis now. So again, remember, I'm rotating the region between the curve and the x-axis. So now I'm taking all of this and rotating around the y-axis. Pause here for a second and really think about what the shape will be. It's fairly easy to draw in the mirrored version, but to really visualize the three-dimensional object in this case is a little bit awkward because the object in itself is a little odd. So if I draw in the mirror image of this curve right there, again, remember that I am actually rotating this solid around. What I actually get is this kind of like weird looking bowl where I have solid walls around one. I have a bowl going all the way around, but it has a hollow center. It's this portion I'm rotating, which means that this center is going to be empty, okay? So a hole that is of this sort of V shape inside. Okay, great. So now if I'm going to be using disks, I have to draw in a typical disk that when stacked up will actually give me this bowl shape. So think about if this is a pancake stack, how would you form a pancake stack with hole in the middle? And let's see if we can draw in such a disk. So what happens here is if I try to draw a disk, I notice that my outer points are going to both lie here. So my disk is going to go from here all the way out to here. I have to connect through the other side. But then what do I do with this empty center? It has to be hollow, which means that my disk actually has to have a hole in the middle. So my disk isn't so much a disk as what we call a washer. You know, washers, the things that you use in construction. It's not a solid disk the way that we've always drawn them up until now. It actually has an opening in the middle. And if you draw it at different points, for example, a disks up here will be, in fact, very, very skinny. There will be mostly holes, whereas the disks further down will be nearly full because the hole here is going to be so little, right? But my general disk will have a hole in it. This is a situation we have not seen yet, and we won't be able to actually set up just yet because we really have to, or at least using the tools we've developed so far, because all that my disk formulas tell me is that I have to think of the width of the disk, which in this case, I can also, of course, give it right there. It's going to go along the y-axis, so I know my integral is going to have to be in terms of y. But then I have to think of the radius of my disk. And it sort of has two radii. It has the outer radius that is formed by the bigger portion of it, and it has this inner radius that forms the hole, which forms the piece I don't want. How are we going to put the two together, this is the topic for next class. So this is just a small preview of how sometimes you can end up with different shapes that you haven't seen before and don't have tools for yet, but we're going to get there. Now, for this question, what I strongly encourage you to do is to draw in cylindrical shells for both of these methods as well, and see if you can comprehend how to do the shells in both of these cases. The second part of this question asks specifically for shells, so I'm going to set it up for shells, and I encourage you to then set the exact same volumes up for disks. Now again, notice the typos here. What I would like to do is have the exact same function, but now I'm going to rotate the region bounded by the function and the y-axis, just to mix it up. So I'm going to be rotating this portion, and I'm going to be using cylindrical shells to draw in. Okay, so what do we have here? First, I'm rotating this about the x-axis. So I'm going to take my function down. Here we go. But again, remember that I'm rotating this portion, not this portion the way that I did before. So this is going to produce kind of the exact opposite of my bowl here. It's going to produce sort of, if you're going to carve the bowl out of wood, it's going to produce what you did not use last time, right? So in this case, it's actually going to produce this region on the outside. So let me once again draw in these boundary points here and maybe introduce this one thing so that we can see how the bowl is formed. And now I have to draw in cylindrical shells. Now remember that the axis I'm rotating around for cylindrical shells forms the core of the shells, which means that my shells have to somehow sit along my axis of rotation, and their heights have to somehow end up on my function in order to actually form the cylinder. Notice here that if you were to sketch disks, you would end up with exactly the same problem as we did on the right-hand side here. Because for disks, I would have an outer disk and I would have to form a hole in the middle. But shells are by their very nature hollow, which will actually be to our advantage in this case. So first I'm going to pick a point somewhere on the curve, let's say, right here, and I'm going to draw the cylinder that corresponds to that point on the curve. Remember that whenever you're rotating around the x-axis, your cylinders are going to span along that axis, so I'm going to have to build my cylinders in this way, which means that if I have a point here, I'm going to somehow form my cylinder to fall onto fall around the x-axis, to be formed, rotated around the x-axis this way, right? Now remember that the cylinders actually have a bit of thickness to them. I should have drawn the point a little bit higher. So there we go, right? And so really think about stacking these kinds of rolls all the way from here. Again, remember they're shallow. They're like cans. They're very, very thin, let's say metal, right? And you're stacking them from all the way over here to shorter and shorter ones, shorter and wider guys, all the way down to here. Each of them with some non-trivial thickness that ends up actually building up in this case. Now, as before, you notice that here we, of course, are dealing with the thickness along the y-axis, which means that my integral is going to be in terms of y. And then I'm going to, as per usual, set up my integral for the cylindrical shells as 2 pi rh times the width, which in this case is dy. So now I simply have to think of what is the radius in this case and what is the height. For this point, and the integral having to be in terms of y, for this point, I note that the height of my cylinder is in fact the x-coordinate, and the radius of my cylinder is the y-coordinate of those points. So the radius is the y, which is what I want my entire integral to be in terms of, and the height is the x. So before I can proceed to really put this together, I have to solve the equation y equals root x in the other direction for x. So I'm going to get y squared is equal to x, which means my height is going to be given by y squared. Okay, so all of this, bit of a work for that. Now, once you plug all of those things in, you will get yourself an expression for the integral that you can then solve. And then, of course, the limits of integration here are also going to be from 0 to 1 because my y goes from the smallest possible cylinder here to the biggest possible here. So again, notice the strength of cylindrical shells here. I did not have to think of whether the inside has to be somehow taken out, like in the case of the discs/washers in the other case. The shallow nature of the cylindrical shells here allowed me to avoid having that headache. Now let's think about how to do this around the y-axis. So again, I'm rotating this region here around the y-axis, right? So I'm going to form the mirror image of this curve, first of all. There we go, something like this. And then I have to think of this shape right here, this sort of inside of the bowl, as being formed out of cylinders. So how am I going to stack my cylinders like the Russian dolls inside each other in order for me to produce this shape? If I am rotating around the y-axis, it means my cylinders have to grow around the y-axis as the core. So this is where they're going to be. And this time, they aren't actually very difficult, I think, to visualize. They will be a little bit more complicated to set up. What you have to realize is that all of the cylinders that you're going to have to build will have this as their base. Okay, so I'm going to sit all of my cylinders along here and then pick a point somewhere on my curve, let's say right here, and the cylinder that will correspond to that will actually look like this. Okay, with some non-trivial thickness to it this way. So if I pick a point further down here, my cylinder is going to be longer and skinnier. And if I pick the points somewhere here, my cylinder is going to be shorter and wider. Okay, but all of my cylinders will actually kind of have this as their base. All of them will sit on top of that line, not on top of the axis, which is something sort of that we're used to in all of the examples before. Okay, so first things first, I noticed that the thickness of my cylinder is parallel to the x-axis, which of course means that my integral is going to have to be in terms of x. And now I can set it up so I have my 2 pi rh times dx, and I have to think of the radius and the height for these cylinders in terms of the given point here. Let's take a minute here and think about that. So what is the radius of my cylinder? The radius of my cylinder is this length right here, which is fairly easy. This is simply going to be the horizontal distance or the x-coordinate of the point. So that is something I can do right away because my integral is in terms of x. So my radius is going to be square root of x. But what about the height of my cylinder here? This is the first time I'm dealing with this not sort of resting its base on the axis, so I have to be a little more careful. This is the height of the cylinder. I know what this length is. I know that this is the y-coordinate of my point, which I actually know to be x to the power of 1/2. So I know this length, and I actually know this length. The second guy is just 1, and between 0 and 1, right? So I know this to be square root of x. I know this to be 1. What I want is this. So take a look at this picture and see if you can see what that will be. It's going to be all of 1 minus square root of x. That's the height of my cylinder here. 1 minus root x. Okay, let that sink in for a second. The height, 1 minus root x. So again, the shallow nature of the cylindrical shells allowed me to set up both of these without having to deal with taking some insides out or whatnot. But sometimes you really have to think about what the radius and what the height are going to be. This is why it's completely essential to draw pictures, because there's no other way you can figure out what the corresponding components will be. Now, next time, we're going to talk about how to deal with rotating not around x and y axis, but around other lines, and also how to deal with cases where we end up with having to subtract some volumes portions out of the total.